We have spent about 2 to 3 videos to discuss what are conservative forces and what are non-conservative forces. So what's the point of determining whether a force is conservative or non-conservative? Well, if a force happens to be a conservative force, we know that we can interpret the work done by this conservative force in a different way. So this is a unique characteristics of conservative force, and it cannot be done for non-conservative force. So we happen to know from an earlier video that gravitational force is a conservative force. So let's try to see whether we can interpret the work done by gravitational force in a different way. And we'll do that using an example. So let's say we have a ball here which is now above the ground, and I happen to throw this ball upwards. Therefore, the ball undergoes a displacement of s, going from an initial position of height h initial to a final position at height h final above the ground. So in other words, we say this object here experiences a change in height, which we can label it as delta h. Okay, so this is a situation. Let's try to determine the work done by gravity when this object here undergo this displacement s. So the work done by gravity, we know that it's just a scalar product between the weight and the displacement. So let's try to determine the direction of weight, direction of displacement, and the angle in between the two vectors. So weight is the gravitational pull exerted by Earth. So in this case, it's pointing downwards. Whereas the displacement, since this object is moving upwards, the displacement is pointing upwards. So weight is downward, displacement is upwards. We know that the angle between them will be 180 degrees. So now let's re-express this equation in a different way. Okay, displacement is upward. So let's re-express it in a different way. We express it as the magnitude of weight times the magnitude of displacement times the cosine of the angle in between the two vectors. So the magnitude of weight, we know that is just mg. Okay, magnitude of weight and magnitude of displacement are both magnitude of vectors, so you have to make sure that the magnitude of weight and the magnitude of displacement must be always positive. So magnitude of weight here, mg, is a positive value. For the magnitude of displacement, in order to obtain magnitude of displacement, which is a positive value, we have to take a larger value minus the smaller value. In this case, the larger value is final, the smaller value is initial. So final minus initial happens to be delta. So we can re-express the magnitude of displacement as delta h. If today your initial is bigger, your final is smaller, then your magnitude of displacement will be initial minus final. But right now your final is larger than initial, so your magnitude of displacement will be final minus initial, which is also delta h. Okay, so you have to look at the situation, which is larger, which is smaller. Next angle is cos 180 degree, as we discussed just now. Cos 180 degree based on trigonometry is -1. So now our equation will be work done by gravity equals to negative mg times the change of height. Okay, so this is work done by gravity, and we know that mg here is positive and delta h here it's positive as well. Okay, it's positive because it's a magnitude of displacement. Magnitude of displacement must be positive. Okay, so positive multiply with a negative sign. Therefore, we know that this work done by gravity, it's a negative work done. We have discussed in the earlier videos that if work done is negative, that means the energy is being transferred out from the body. So you can think of it as the body lose an amount of energy out from the body. Okay, energy is coming out from the body. But now we are trying to give a new interpretation to this situation here. Instead of saying that energy is being transferred out from a body, we will say that this energy will be transformed into another form to be stored in the system. Okay, instead of saying that it's out from the body, say it will be transformed into another form to be stored in the system. And what is another form that we say just now? The another form is called the potential energy. And since we now reinterpret energy transfer out of the body as energy being transformed into potential energy, therefore we will say that this object here experiences a change of potential energy. And so now we will provide a new interpretation, which is the potential energy changes when this object undergoes a change in height. So potential energy, change of potential energy is just potential energy final minus potential energy initial. In this case, I put a subscript G to represent that this is gravitational potential energy. So change of gravitational potential energy is equal to the final gravitational potential energy minus the initial gravitational potential energy. So you learn from SPM that gravitational potential energy is just mgh. So this will be mgh final minus mgh initial. Both terms here share the same m and g. So let's factorize out m and g. Then you get m and g bracket final height minus initial height. You happen to know that final minus initial is just delta. So you can re-express h final minus h initial as mg delta h. Okay, so now you see that the work done by gravity, it's very similar to the change of potential energy. To be more specific, if you take the change of potential energy and you negative it, you get work done by gravity. Or if you negative the work done by gravity, you get the change of potential energy. So definitely the work done by gravity and the change of gravitational potential energy share a close relationship. And what's the relationship? The relationship is that work done by gravity is equal to the negative of the change of gravitational potential energy. So this is an important relationship because now we can re-express it like this. We can say work done by gravity, W subscript G is equal to the negative of delta U subscript G, negative of the change of gravitational potential energy. So this is something very important because what I'm trying to tell you is if your work done here is a work done by a conservative force, you can re-express the work done by conservative force as the negative of the change of potential energy right now. So we are re-expressing work done by conservative force in terms of the change of potential energy. So this is what we say a new interpretation to the situation. So this will be a very important equation. Work done by conservative force is equal to the negative of change of potential energy. And we will analyze it for the gravitational situation. And we will also analyze it for another conservative force, which is the restoring force of the spring.